So today we're going to talk about section 2.4. Okay? Section 2.4 talks about measures of variation. We talked last time about measures of central tendency, and in Algebra 2, when we talk about measures of central tendency, or even Algebra 1 or lower 8th grade, you talk about mean, median, and mode, right? Well, when we talk about it at a high school or junior high level, we actually include 4: mean, median, mode, and range. Those are the measures of central tendency that we talk about. But what's interesting is that range is actually a measure of variation as opposed to a measure of a central tendency. Okay? So, the best part about range is that you already know how to do it, right? The maximum data entry, subtract the minimum data entry, just the subtraction to figure out what's the range of data that you have. Subtract the smallest from the biggest. Yes? Okay, so not a big deal. There's some examples here if you wanted to look through them. 2 numbers, subtract, boom, boom, done. Got it? That one's not very difficult, okay? This, however, is brand new. Okay? Variance and standard deviation. When I'm doing this problem or these problems, either variation, standard deviation, and then some stuff later on that we'll talk about, my hardest problem is remembering what the letters stand for. That's my biggest problem, okay? So that's why I was telling you before, sometimes I have these formulas written out on the side, or maybe a copy of this page, and I have each of the variables defined so I remember what they stand for, okay? So first of all, you need to know what deviation is, okay? The deviation of an entry, X, that's what each entry is called, an X. So the deviation of each entry in a population data set is the difference between the entry and the mean, which is the mu of the data set. Okay? So if we have this particular data set right here, okay, the one that's right here, and we add them all up and divide by however many, because that's, remember how we find the population mean, add them up and divide by how many, we would get 41.5. Okay? So to find the deviation for each specific entry, we take the entry, so in this case 41, and subtract the mean, 41.5. 41 minus 41.5 is negative 0.5. So for deviations, especially deviations, it is absolutely positive for the number to be positive or negative. Okay? 38 minus the mean, 38 minus 31 or 41.5 is negative 3.5. And so on all the way down. Does that make sense? So finding individual deviations, that's how you do that. Excuse me. Okay? Now, a population variance, that's the deviation. For a population variance, first of all, you have to find the sum of squares of the deviation. So we just found all the individual deviations for each individual data point. Then you have to find the sum of that. Now in this particular problem, it's 0. That's fine. It's not always that way, but in this particular problem it is. Okay? So find the sum of the squares, which is the sum of the squares of the deviation. That's denoted by SS of x. Okay? That's used several times in this section, and so I really need to have some sort of marking for myself. Let me make that real quick. For this SS of x right over here, sub x, excuse me, so I remember where to find the sum of squares, because I'm probably going to have to look back. Okay? I'm probably going to have to look back to remember what that means. So the sum, remember sigma signifies sum, the sum of the squares. So finding all these and squaring them. Does that make sense? Now to find the population variance after that, we find the sum of squares, and that is divided by n, which is the number of terms in the population. Do you remember that? Now look what that's equal to. That's equal to sigma, that's the lowercase sigma, sigma squared. Well, what if we were just trying to solve for sigma? If I'm trying to solve for sigma, what would I have to do to this side of the equation? Square root it, right? Well, that's interesting because that is a thing also. The square root of the population variance is called the population standard deviation. These deviations up here are asking for individual deviations as a group. Okay? The standard deviation is saying what is the general deviation for all of the sets of data, or all the data points as a set. Okay? So here's some observations about standard deviation. The standard deviation measures the variation of the data set about the mean and has the same units of measure as the data set. That's what I was trying to say before. In layman's terms, here's the mathematical definition. Okay? The standard deviation is always greater than or equal to 0. So when sigma equals 0, the data set has no variation, so all entries have the same value. You okay with that? And last, as the entries get further from the mean or more spread out, the value of excuse me, the value of sigma increases. But that would make sense, right? If it's more spread out, that value would be bigger. Okay? Okay so far? So, on page 84 in your book, there's this guideline section. Remember, we've talked about this guideline section before. It kind of gives you some steps to get through some of these problems that some people find really helpful, especially when it's something they're not familiar with. Okay? So, when you're finding the population variance and the standard deviation, it gives you words and it gives you symbols. Okay? So, these symbols say find the mean of the population data set. We know how to find the mean. We've been doing that for a while. Okay? We find the sum of the terms and divide it by the number of terms. Find the deviation of each entry. So each x value minus the mean. Okay, that can be positive or negative. Then we want to square each deviation, square each number. Okay, then add them all together to get the sum of the squares. Divide by n, the number in the population, to get the population variance. And then square root it to find the standard deviation. Does that help a little bit? Okay, good. So this, if you want to look at example 2, if you're struggling with that a little bit or need a little bit more advice or help, look at example 2 because it kind of takes you through that. We're going to come back to example 2, so I'm not going to show you it right now. I'm going to show you some other stuff first and we'll come back to it, okay? A new definition at the top of page 85. Sample variance and sample standard deviation is a sample data set of n with the entries listed below. If you look at the formulas for population standard deviation and sample standard deviation, they are almost exactly the same. Okay, we're still finding the sum of the squares of each term minus the mean, which we called the deviation, right? We're finding the sum of the squares of deviation and dividing by a number. When we find the population, we divide it by the number of the population. When we're doing a sample, we divide it by the number in the sample minus 1. Okay? Again, here's some guidelines of how to do that, how to take care of that information. Okay, so I suggest you look back at that if you need to. Then there's this really sweet formula chart right here. Okay? It's saying variance, depending on whether we're talking about a population or sample, it defines all these for you. Okay? Sigma squared is the variance, or s squared, depending on if it's a sample. The standard deviation is sigma, the lowercase sigma, or s. The mean is mu, or bar x bar, excuse me. The number of entries is a capital N or a lowercase n. The deviation is each individual data point, the x minus the mean. And then the sum of squares is defined for each one of those as well, population and sample. So I refer back to this particular chart a lot because, you know, it's kind of new. So I refer back to it so I remember what everything stands for. Okay? Interpreting standard deviation. These are really good examples to look back at. Example number 5. But let's talk about these 3 right here. Okay. The mean of this sample data is 5. The standard deviation is 0. Why is it 0? Because there's only one kind of data and it's all 5s, right? The mean of this data is also 5, but the standard deviation is 1.2. So does that make sense that it would be kind of close to 1? Or excuse me, a little bit greater than 0 because it's kind of spread out a little bit? But look at this one. This mean is also 5, but look how far apart they are. So does it make more sense that the standard deviation would be greater than this one right here? Because all the data entries are further apart. Does that make sense? Okay, any questions about that? Okay. This is important. You may want to copy this down. You may want to put this in notes yourself. You may want to make a copy of this. But this is a standard bell-shaped distribution. Okay? Many real-life data sets have distributions that are approximately symmetric and bell-shaped. For instance, the distributions of men and women's heights in the United States are approximately symmetric and bell-shaped. Later in the text, you'll find bell-shaped distributions in greater detail, but for now we're going to look at the empirical rule and let that help us see how valuable the standard deviation can be as a measure of variation. Okay? Here's what I need you to know about the bell-shaped curve. All right? According to the empirical rule, 68, 95, 97.7 rule, 68% of the data is within one standard deviation of the mean. Here's the mean. Okay, one standard deviation to the left and one standard deviation to the right. This is 68% of the data. Okay, one more standard deviation to the left, one more standard deviation to the right, so a total of 2 to the left and 2 to the right. 95% of your data will fall in here, in these sections right here. Okay, then one more standard deviation both left and right. Between these two data points right here, 99.7% of your data will fall within these points. Okay? Does that make sense? So to go from 68 to 95, that means we've got 27% for these two sections. So that's why they're labeled 13.5% each. Does that make sense? And then to go from 95 to 99.7, that's what, 4.7% more data, which is why you have 2.35 here and 2.35 here. Okay? That's what makes it bell-shaped or symmetric. Now, do you see why this is also called the 68, 95, and 99.7 rule? Because it's 68, 95, and 99.7. Okay? Any questions about that? Okay. I think that this is called Chebyshevs Theorem. I remember calling it Chevy Chase's theorem when I was learning this the first time. Please tell me you know who Chevy Chase is, even if you don't say yes. Okay. Wait, do you really know who he is, or you only said yes because I said? You know? Okay, all right. Chebyshevs Theorem says a portion of any data set lying within k standard deviations, when k is greater than 1, of the mean is at least, oh look, another formula, 1 minus 1 over k squared. Okay? Empirical rule only applies to symmetric distributions. So what if it's not bell-shaped or symmetric? Where do we get information like that? Well, we use Chebyshevs Theorem. Okay? So here's an example. Example number 7 in your book talks about Chebyshevs Theorem. You can look at that. Standard deviation for grouped data. That sure looks a whole lot like stuff we've already done, doesn't it? All those variables. Okay? Excuse me. When you do this, I want you to remember that n does equal the sum of the frequencies. So keep that in mind. Okay? Let's go back. I think I want it ready to go back. Let me look one more page. Nope, not ready to go back yet. Sorry. Coefficient of variation. Coefficient of variation, or sometimes known as CV, although CV is quite a few other things, so we'll probably just call it coefficient of variation. Population versus sample. What are the formulas? How are they in common? Are they in common at all? Are they close in common, or what? What does sigma and S mean? Standard deviation, whether we're talking about population or sample, right? And then what about X bar or mu? That's mean, right? So it doesn't matter if you're doing population or sample. You have to keep that in mind when you're getting information, but you're taking the standard deviation and dividing it by the mean and then multiplying it by 100 to get the coefficient of variation. Okay? Now I want to go back and look at example number 2 because there's something I'm going to show you. Okay? I cannot imagine any job. Now, please understand I don't know all the jobs. Okay? So keep that in mind when I say this. But I cannot imagine any job where you would have to know how to do these kind of statistics where that you wouldn't have a calculator. Okay? Or a computer program to help you out. So I want to show you how to do this in the calculator so you know the steps for that as well. Yes, you know it's important to me that you know how to do it by hand, but we can do it in the calculator as well. Okay, so I went to a new document and I'm going to listen spreadsheet number 4. Okay, we're only making one column. We're only listing one column of information. I'm going to use salary information from example number 2 in your book in section 2.4. So I don't need to label this as anything. I could go up there and label it as salary or X or something like that, but I don't need to since it's the only information I'm putting in the table. Okay, so I'm going to enter all of these data points into my calculator real quick. 41, 38, 39, 45, 47, and 41, and then 44 and 41 and 37 and 42. Okay, does that make sense? Now from below the column, I entered to get that information in the column. From that place right there, I'm going to go to menu and statistics and statistical calculations, stat calculations, and then I want to choose one variable statistics. Okay, one variable statistics. I want to use one list. Okay, and all that stuff is already right, exactly how it is. So I'm going to say okay. So look what it told me. I'm going to arrow up real quick. It's telling me, okay, we're doing one variable statistics or one variable, statistics. Look what it told me first. What's that? The mean. Okay, it did it for me. Look at what it told me next. The sum of the mean. Right? It even told me that already in my table, so I know that that's correct. This is all of these squared and then summed. We'll use that, but not yet. Okay? Then it tells me SX. What does S mean? Do you remember? Standard deviation of the sample. Okay? And then it also gives me sigma X. This is my standard deviation of my population because I have all of it there. All of the data points. That's the mean. Excuse me, the standard deviation. Now it says 2.97 in the book. It tells me it's approximately 3, but we know 2.97 is approximately 3, so we're good. Okay. It also tells me the number of terms, and that's 10. This more goes till tomorrow, but I'm going to go ahead and show it to you today since we're already here. Okay. This shows me the minimum. It shows me quartile 1. It shows me the median, it gives me quartile 3, and it shows me the maximum. Okay? And then SX, you remember what that means? Remember, should we look it up real quick? Let's look it up. Turn back. Oops, that's the wrong page. The sum of squares, oh, you can't see that. Sum of squares is denoted by SX sub X. So it tells me that right here in the calculator, 88.5. But using their calculations, we know that 88.5 is this SX, so we're good. I keep saying SX. You know I'm trying to say SSX. I'm just not doing very well. I'm sorry. Okay? And that's all the stuff that it tells me. That's almost everything I need to know. Almost all these formulas that we learned today are in the one variable statistics in your calculator. Does that make sense? Yes? Okay. So that's how we can find it in the calculator. Like I said, these quartile 1, minimum quartile 1, medium quartile 3, and max is mostly for tomorrow's stuff that we'll talk about tomorrow, but I just wanted to show it to you, talk about it a little bit since it was here in the calculations that we made with our calculator today. We'll refer back to these tomorrow. You okay with that? Okay, so that is section 2.4. We will talk about 2.5 next time. Are there any questions? Peace.